In this video, we are going to first start off with an example, which will be a review from yesterday, and then I'm going to expand on the question and ask you some more questions, which will bring us into what we're going to be learning and exploring today. So let's start off here. It says, when a metal is struck by a photon with a frequency of 8.23 times 10 to the 14 hertz, the metal emits an electron with a maximum speed of 2.45 times 10 to the 5 meters per second. What is the work function for this metal? And it wants our units in electron volts. So let's start off by writing down what we know. I know my frequency is equal to 8.23 times 10 to the 14 hertz. I know my velocity is equal to 2.45 times 10 to the 5 meters per second. Now, I also know from before we have a formula that works like this, where we know my kinetic energy of the electron released is going to be equal to Planck's constant multiplied by my frequency of the photon coming in, and we're going to subtract that from my work function of the metal. And that's what we're trying to find in this case, is my work function of the metal. Well, we also know that kinetic energy is equal to 1 over 2 mass times velocity squared. All right? So now we're trying to isolate for my work function, so let's isolate for that work function. So we're going to rearrange my formula, and I'm going to end up getting okay. So now we're going to use our substitution, substitute everything we know. We know Planck's constant is 6.63 times 10 to the negative 34. And that's joules seconds. And we know my frequency is equal to 8.23 times 10 to the 14 hertz. And we want to subtract 1 over 2. My mass of an electron is 9.11 times 10 to the negative 31, and that is kilograms. And we know my velocity is 2.45 times 10 to the 5 meters per second, and we want this squared. So when I calculate all that, I'm going to end up getting 5.18 times 10 times 10 to the negative 19 joules. But we wanted my answer in electron volts. So what I must do is we have to convert to electron volts. So I'm going to divide this by 1.6 times 10 to the negative 19, and that is joules per electron volts. We look at my unit cancellation, my joules cancel off, I'm going to end up getting 3.24 electron volts. Now, if we were to graph this, we get something that will look something like this. Okay, where my y-axis is my kinetic energy, my x-axis is going to be my frequency. Now, over here we have my y-intercept, which is my work. Okay, so it's my work function of the metal. And this right here is my frequency, which we need to eject anything. So anything right here is the energy level, so see all the way to the work function, is the energy level needed to eject an electron. Now, if I was to make an equation from math 10 or 20 for this, we would get y is equal to mx plus b. So my y is my EK, is equal to, well, my x value is my frequency, and my y-intercept, which is b, is going to be negative minus my work function. And here, we're going to have to now look at what is my slope. My slope is my Planck's constant. So essentially, all that we're doing here is we're saying the energy of the photon subtract the energy of the metal required to release an electron is going to be equal to the kinetic energy of the electron. Now, how did we know Planck's constant? How do we know this slope? What experiment did we do to help figure out Planck's constant and that slope? Well, I look at this over here. We're going to do a simplified version of Millikan's experiment. In this experiment, Millikan was able to determine the energy of the electrons that were emitted from the incoming photons on a source of metal. So how did he do that? And why is this important? Well, let's first look at how he did that. First of all, let's ignore this power supply. If I have incoming photons here, they're going to hit this metal side, right, this metal plate here, and produce, if it's a strong enough frequency, electrons to go, and they're going to end up going to this side of the collector. And that's going to end up creating a current. Now, this is kind of what Millikan did. He put a power supply here, and now let's make this side negative and this side here positive. Now, if this is negative, that's going to try and resist these electrons from going to the plate. So he kept on increasing the voltage at small increments until there was absolutely no current. This is called the stopping voltage. So why is that important? Well, we know from before that volt is equal to my energy divided by my charge, right? So we know the charge of an electron, and these are electrons moving through. Then we know my energy, in this case it's going to be kinetic energy, is equal to my volts times the charge of the electrons it's trying to stop. So in other words, by looking at this here and going back to our formula, EK is equal to HF minus my work function. Now we were able to figure out what my energy is, which is volts times my charge. And then we know what the frequency is for when eventually an electron was emitted. And then we were able to know the work function and everything like that. So then it made it very easy for us to find what Planck's constant was. So our final result from our experiment is this formula right here, which is extremely powerful. Kinetic energy, the maximum kinetic energy, is equal to my electron charge multiplied by my voltage stopping. In this example, we have a blue light that shines on the metal surface as shown in your textbook and causes the photoemission of electrons. If a stopping potential of 2.6 volts is required to completely prevent the electrons from reaching the collector, determine the maximum kinetic energy of the electrons. Express your answer in units of joules and electron volts. So let's first look at what we're given. We are given our voltage or potential difference of 2.6 volts. We are trying to figure out my kinetic energy of the electrons. So we know the energy is equal to the amount of volts it takes to stop a charge. And that will be the kinetic energy in this case. So let's substitute in here what we have. So we end up getting 4.16 times 10 to the negative 19 joules. So we found our units in joules, but now we also have to figure out in electron volts. So to figure it out in electron volts, all I'm going to have to do is divide this by 1.6 times 10 to the negative 19 joules per electron volts. Now if we look at that, that's just going to give me 2.6 electron volts as an answer. So these here are my two answers for the question. So in this part here, I'd like you to pause the video and try and figure out or show how Planck's constant is equal to my charge of electron multiplied by my stopping potential plus my work function divided by the frequency of the photon entering. And why is this important? I want you to do it two ways, by looking at the graphs that we did in the very first question of the video and by looking at how I was explaining things throughout, and see if you could try and explain this little section here. So pause the video, you could either call a friend or work individually to try and figure that out. Here are two questions for you guys to work on by yourself together to see if you're understanding what we are doing. These are the answers to those questions. Now, here is our very last question of the day. In this example, we have aluminum with a work function of 4.08 electron volts being illuminated by a wavelength of 125 nanometers. It first wants us to calculate the retarding potential and then the speed of the ejected electrons. Let's first write down what we know. I know my work function is equal to 4.08 electrons volts. Now if I multiply that by 1.6 joules per electron volts, that will convert this into my joules, which will end up giving me 6.52 times 10 to the negative 19 joules. We also know my wavelength is equal to 1.25 nanometers, which is equal to 1.25 times 10 to the negative 7 meters. We're trying to figure out first my retarding potential, or my stopping potential. And secondly, we will try and find out is the velocity of the electrons. So let's first look here. We know my energy, my kinetic energy of the electrons is equal to Planck's constant multiplied by my frequency, so that's the energy of the photon coming in minus the energy of my work function. But we're not given the frequency here, so we're going to have to rearrange this with the energy with the speed of light divided by my wavelength, and that's going to be the energy of the photon coming in. And we're going to have to change the energy here, which is the energy required to stop it. So we're going to look at my voltage multiplied by the charge of the electron. So that's the energy of the electron. This part here is going to be the energy of the electron leaving or being emitted, and then we want to subtract the energy of our work function. We are trying to isolate here for, once again, my potential, my stopping potential. So I'm going to end up rearranging this formula. I'm going to have, and we're going to divide this all by the charge of an electron, which is going to give me 6.63 times 10 to the negative 34 joules seconds multiplied by 3 times 10 to the 8 meters per second. And all of that's going to be divided by 1.25 times 10 to the negative 7 meters. And we're going to subtract this all by my energy of the metal that's required to release it, which is going to be 6.52 times 10 to the negative 19 joules. And all that's divided by the charge of an electron, which is 1.6 times 10 to the negative 19 coulombs. So when I plug this all in, I'm going to end up getting a total of 5.865 volts. Or in other words, since we're only using 3 digits, we're going to end up getting 5.87 volts. To correct significant figures. Now we want to find my velocity. And I know my kinetic energy is equal to qv, but it's also equal to 1 over 2 mass times velocity squared. And we're going to try and isolate for velocity here. So when I do my little rearranging, I'm going to end up getting something that looks like that. Now I could just plug in everything I know. So I'm going to have 2 multiplied by the charge of electron, which is 1.6 times 10 to the negative 19. And that's coulombs, multiplied by my potential difference, which is 5.87. That's my stopping difference. I would try and use this one here, the non-rounded one, when I'm plugging it into my calculations. Then I'm going to divide it by the mass of electron, which is 9.11 times 10 to the negative 31 kilograms. So when I calculate all this, I'm going to end up getting 1.44 times 10 to the 6 meters per second. And that is going to be the speed of the electron being emitted or released by the photon. So this is what we've learned so far, are the most significant results of the photoelectric effect. Number 1, electrons are emitted from the photoelectric surface when the incident light is above a certain frequency, called the threshold frequency. The intensity, brightness of the light has no effect on the threshold frequency. The threshold frequency at which the photoelectric emissions first occur is different for different surfaces. So each surface has a different work function, or threshold frequency. As the retarding potential that applies to the anode is increased, the photocurrent decreases, regardless of the intensity of the light. So remember, intensity of light doesn't matter, it is the frequency of the light. If different frequencies of light, all above the threshold frequency, are directed at the photoelectric surface, the cutoff potential is different for each. The higher the frequency of the light, the higher the cutoff potential. And then lastly, when a photoemission is occurring, the release of the electron is immediate.